Hello, Lavanya. Only you are there. Good evening. So wait for 3 minutes. I will start then. Well, I don't see any other people. Only two of you are here, and I will start. It's 7:05. Mm, I don't have any. I mean, topic to discuss today. Few assignment question from assignment number 4, assignment 5 and 6. I took some specific question which I liked. That's it. Not all. But yeah, I have more than 17, 18 question, and I will try to solve those. These are very easy and discussed by ma'am actually, and I have also sometime discussed. Should I wait for or not? Let's show the slides. Yeah. Go ahead. These are all assignment question. You already know. Okay, no problem. Okay, hello everyone. Good evening. And this is day 8 reaction mechanism in organic chemistry. Today's topic is just some questions. Easy. So, this is a question which is based on Hammett plot, right? Now, if I read the question, what is it? The correct statement for the given reaction is the rho value of minus 4.48 is R. We have given a reaction which is a carbon chlorine bond is substituted with carbon oxygen bond alcohol. So it's a typical substitution reaction, and given a rho value of minus 4.48. How do you interpret the value? Well, it's a negative rho value is shown. Now, actually, this mechanism is very easy. From the just by look of it, and you can say what will be the mechanism, what will be the correct statement. Even though we know it, we will try to get the significance of this value, rho value. Okay. So before I read the options which are given, let's try to analyze. I mean, what's the rho value mean actually? So we have our friendly whiteboard. So we have plenty of time, I think. So if we follow our discussion that typically x and y axis, we should label everything at least. So log of kx, log of kx by kh. Okay. And here, let's say this is the position of hydrogen. Let's say we denote as 0, and this is electron withdrawing group EWG, and this is electron releasing group, right? I don't have mouse, that's why I'm having some problem here. Now the rho value is negative minus 4.48. So what we can expect? A line passing through like this. I put the slope very 1 second. Please join little fast. Now this is the rho value. Oh, sorry, so this is my picture is extremely wrong, confusing. This was a positive slope. Okay, so I have what I have is a negative slope, so it's like this. It's a straight line passing like this. Now electron releasing group, for example NH2 group having high rate compared to hydrogen, so there is a point. Okay, now when you have electron withdrawing group, the rate is slow, so that's what it means. Now based on this, we can see there is a formation of, so rate is high when there is electron releasing group, so we can think of X here, which is NH2 group, and since the rho value is very, magnitude is high though it's negative, so we can think of there is a positive charge formation, very high positive charge, which is delocalized through this benzene ring, and an electron releasing group will stabilize that releasing group. So here, so we can say that based on this rho value, it follows a formation of fully developed positive charge. That's why we can think of it's an SN1 type mechanism. So the first statement itself, we can say this is the correct statement. The reaction follows an SN1 mechanism. Okay. Now let's read the second statement. The reaction rate will significantly increase with increase in solvent polarity. This statement, now from the mechanism SN1, we know that there will be formation of two charged species here. Carbocation plus charge and then Cl minus. Both will be hydrated by the water molecule. Now if you increase the solvent polarity, it will stabilize this species, right? The intermediates and the transition state will be stabilized because those are more polar than the ground state. Accordingly, the rate will be faster, meaning that if I draw these things in a plot here, so again there will be two axes here. This is a reaction coordinate along the x-axis, and this is the energy, potential energy. Now let's say these are my ground state, and when the solvent, so there will be carbocation intermediate here, and then the second step, and sorry, and then the second step it will give me the product. Now this when you have more polar solvent, basically it will reduce this step. Ground state will be less lowered, but the transition state will be lowered at greater extent because those are charged species, polar species. So if you increase the solvent polarity, the intermediate and the transition state will be lowered in energy. Overall, there is a rate increasement. That's why we say the reaction rate will significantly increase with increase in solvent polarity. Okay, this is also seems correct, right? Third, the reaction rate will not change with an increase in solvent polarity, which is not correct, I think. Because if you, it's an SN1 reaction, there is a charged species are involved, and that's why this statement is wrong. If you increase the solvent polarity, the reaction rate of course will change and it will increase. The reaction rate will decrease with increase in solvent polarity. This is also not the fact because the ground state is uncharged, whereas the intermediates and transitions to charged species. So there is a solvent polarity will have increase in rate. The reaction follows an SN2 mechanism. No way this is possible with this 3 pH group. It's not even close to an SN2 mechanism. Overall, if I conclude this slide, the first two options are seems correct. That is, the reaction follows an SN1 mechanism. The rho value also suggests there is a fully developed positive charge stabilized by the electron releasing group will be in place of X. Second, the reaction rate will significantly increase with increase in solvent polarity. So this is the fact. I hope this is a very basic simple question on rho value. Let's go to the second slide. This is also very simple question. Here, what you see is that correct match of solvents in column A. There is a solvent given, cyclohexane, chloroform, water, and acetonitrile, with the equilibrium constant K equilibrium in column B. So, I mean, based on solvent, which form, whether this enol form or this keto form will be stabilized. Now, as if you compare this value, cyclohexane, chloroform, water, and acetonitrile, what value? Like epsilon value, dielectric constant, polarity. So we understand that water is the strong and most polar here. So water will shift this equilibrium to the right side. It will stabilize the this keto form here rather than this enol form. Okay. So we expect a value of very high for this equilibrium when there is water as a solvent. So water, of course, so based on this value 1.7, 6.0, 910, 148, so 3 will go with C. So water will be the highest, for water it will be the highest equilibrium value, K equilibrium. Now the next which has is like chloroform, I don't think so, cyclohexane no, acetonitrile. So after water, acetonitrile is the most polar. So again it will have a high value. Of course, then the next highest value is 148. So 3 goes with C, 4 goes with D. And between cyclohexane and chloroform, CHCl3 has some dipole moment. So it will be much more, it will give much more higher K value, equilibrium value. So it will go with B 6.0 and cyclohexane will go of course 1.7. So overall the answer is just as it is, like 1 with A, 2 with B, 3 with C, 4 with D. So this is a very simple question based on solvent polarity, which form it stabilizes. And then let's go for third form. Now I have a question on this. Why do you think this keto form is much more stable than this enol form, or how it is happening? See, the both has some advantage and disadvantages in terms of thermodynamic stability. This keto carbon oxygen double bond is much more higher strength than the enol carbon oxygen double bond, and this has a dipole moment. So this dipole moment, so this will interact with the polar solvent. That's why it is having this effect. Okay, so water is polar, and this dipole moment, it will have dipole moment, so much better. So it will have the much better K equilibrium value, much stability. Another thing we can say. Whereas enoform gain stability from its aromaticity here, which are there, but it will be stabilized in mostly in cyclohexane. So depending your which form you want more, you can choose your solvent accordingly. Okay, so these are the two factors. Interesting. Let's go to the another question. This question is very easy and nice to follow. This is based on the my earlier question on SM1 reaction. So let's look at the reaction. First one, which is a simple pericyclic reaction, 4 plus 2 cycloaddition. Now in the it's a concerted mechanism. There is a no polar intermediate species are involved. So let's say there are ground state and then the excel and then the transition state and then the product. Now, since both ground state, transition state, and the product all are neutral, I mean neutral in the sense there is not so much charge separations are there. So, any solvent you take, you increase the solvent polarity, it will have a very little effect on both the ground state and the transition state or in the product. Overall, this has a solvent dependency is very insensitive. I would say insensitive. So if you see the solvent dependency in the right column, you see first is lying slightly favored, no. Insensitive to solvent polarity, this can be the case. Disfavored by polar solvent, no, there is no concept. Strongly favored by polar solvent, there is a little dependency on solvent polarity. So the best matches is 1 with B. So it is insensitive to solvent polarity. Let me take one of our friend. So here we see that the option 1 goes with insensitive to solvent polarity. It's the least sensitive because if you see the mechanism, this pi electron will come here, this will form bond with this alkene and this will go. So overall it has insensitivity to solvent polarity. Now I can go one by one, but let me take rather this 3. So this is a ground state of the molecule like tertiary chloride and solubilizes and forms alcohol. The ground state is neutral, there is no charged species. Whereas in the transition state or in the intermediate, again we will have, just a second. In the transition state or in the intermediates, we see there is a polar species are involved because the carbocation will form, say tertiary species, tertiary carbocation is stable. And thus what we expect, if you increase the solvent polarity, it will stabilize the transition state more. So that's why we think of that it should have higher rate. I mean the rate should be slightly favored by, not slightly, strongly favored by polar solvent. So the best option which is matches it is D, I think. So it will strongly favored by polar solvent. So 3 goes with D and 1 goes with B. Now you see the option number 4 here. So the ground state is this time charged, like ammonium salt, NMe4 plus, and then base is hydroxide. So any polar solvent will, and what happen in the transition state, this charge will get dispersed. So the charge are more concentrated on the ground state rather than in the transition state. So charge will dispersed in the transition state. It will be SN2 type mechanism. So what happened? The ground state is more stabilized than the transition state. And the fact, what will happen is that the polar solvent will stabilize the ground state more than the transition state and the rate will be slightly disfavored. So 4 goes with C. Let me explain this all the facts I'm saying actually. So clear the frame. Every time this figure will be there, of course. Now here is, now what I'm saying, NMe3 plus and OH minus. Okay, let's say this is the first, okay, ground state, all the molecules are here, and let's say I have a very high path and this is the product. Now NMe3 plus and OH minus is there, so any solvent polarity whatever it is, it will be here. Now if you increase the solvent polarity, what will happen? It will stabilize the ground state much more in a higher extent. Let's say it will decrease by energy this much extent. Whereas the TS, because the charges get dispersed, the lowering of this will be less. It's this much only. So overall you see there is a increase in activation energy. Overall I can see there is an increase in activation energy. So if you increase the solvent polarity, so the rate will be slower. So this was the second case if you increase the solvent polarity, and for the first case when there is less solvent polarity it is this much. So this is not in scale, so don't think it is a as it number. So the second value, let's say 1 here, and this is 2 here. So if you increase the solvent polarity, so the activation will be very high here because of this case. That's why we see this fourth option will be disfavored by polar solvent. And this very simple reaction, again a substitution reaction, bromine is substituted with alcohol, OH group, water. And since there is the ground, I mean the initial reactants are not charged, but in the transition state there will be slightly charged dispersal, like there will be CBr delta plus delta minus, and then H2 will be also will be have some delta minus charge. So it will slightly favored by polar solvent. Okay, so this will slightly favored by polar solvent. Overall, if I show the answer, I can use this actually, right? So it will be disfavored by this, and this will be slightly, sorry, it will be this, and what I have is this will be insensitive. Next, let me take another arrow, and this will be strongly favored. Okay, so this is the answer for this question. Okay, the first three question I discussed. Now I will give you some time to think about this. This I have ma'am has discussed thoroughly in the classes, and I have also discussed this question a lot. So the correct Hammett plot for the given reaction is, I didn't show the four option here, but I want to give you some time and think what will be the plot. Just say me the row values, positive, negative, what will be the case. So let me, I think you can see the reaction. Uh, this NH2 group will attack here and then this form in. Okay. Let me see how many of you are here. There are 6 of you. That's good. Please try to answer that question. This is the question. Okay? So what will be the correct Hammett plot? Any answer? Just you can type it in chat box or just unmute yourself and say it. How it will look
Sir,
like. Yes, Venkatesh.
sir, electron withdrawing group will increase the reaction. So rho value will be positive, sir. Positive.
Row value. I am writing in the chat box. You said row value will be positive.
Yes.
Anyone else? Have you solved this question in the assignment? Anyone? Lavanya or Christina, Dharani, Pallavi? First of all, say the way I am explaining, is it understandable to you or it is too easy or too difficult? Rho value positive electron return group increase the reaction rate. Rho positive for releasing group. Yeah, perfect. So yeah, so all of you seems that you are aware of it, and but you are saying partially. I mean, you're not doing the full picture. You are right. That is absolutely right. Rho value positive for releasing group. The second part, I mean, your answers are correct. Make it complete. Just make it complete. So what's the interesting thing of this reaction, of this question actually?
The initial first step attack of amine group, amine
Yes.
group on the carbonyl carbon very fast,
Then
and then the next step, the dehydration will be slow step, rate determining step.
okay.
Dehydration. Sir, correct, sir?
So is it true for both electron withdrawing group and electron releasing group?
Sorry, sir, electron releasing group. Electron releasing group.
Okay. Uh, so Venkatesh, you have written rho value positive, electron withdrawing group increases the reaction rate. Now, if I ask you, if there is a, let's say, electron withdrawing group NO2. So imagine I have NO2 group. So how do you think it will increase the reaction rate? Pallavi has answered rho positive for releasing group. Can you justify, Pallavi, how do you think it will the rho value will be positive for releasing group?
Sir, if X is the electron withdrawing group, the electron flow away from the carbonyl carbon. So carbonyl carbon become positive, more electropositive. That means more electrophilic. Then amino group with lone pair it attacks quickly. So electron withdrawing group will increase the reaction rate on that basis.
Okay, no, yeah, go ahead. Okay, so let me explain a little bit further. So, see, the interesting point of this reaction is that it has a change in rate determining state. So that's why I have shown here, hint is the rate determining state. So it involves both rho value positive and rho value negative. So that's what I wanted to, I mean, here. So the interesting part is that there is a both rho values, like positive and negative, are all together in this reaction. I mean, if you plot it. Now, if you see the reaction, I mean plot, then it will, you see a, how do I say this? It's like a hill kind of thing. Okay, hill is like from, then there is a jump. Okay, so let me describe it. Imagine there is a NH2 group, electron releasing group. Or imagine there is a methoxy group, OMe group. Or imagine there is a hydrogen group. Now, when there is NH2 group or OMe group, this NH2 and OMe all will do pushes the electron density from here via resonance to this carbonyl carbon, right? So as you move more electron density here at the carbonyl center, the attack of this amine electron to this carbonyl group will be difficult, right? So imagine you have NH2 group or methoxy group, which will increase the electron density at the carbonyl center. Therefore, the attack of this amine will be difficult. So this is the rate determining step. The attack itself is the rate determining step, right? So now if you compare amine group, methoxy group, normal methyl group and hydrogen. So you see what will happen? The hydrogen will have the highest rate. So remember, electron releasing group are this here, releasing group, and withdrawing group are here. And let's say there is 0 here, and of course log of kx by kh in the y-axis. Now NH2 group, let's say it will have a slower rate. Rate determining step is the attack of this nucleophile. And then what will happen? There is a methoxy group, then the methyl group, then there will be hydrogen. So NH2 group will increase the electron density more to the carbonyl center, and the reaction will be slow because it will increase the electron density there. If you have hydrogen, it will have the highest one. So let's say this here. So we expect a rho value positive here. So electron releasing, So electron releasing group, we expect a rho value of this, a positive rho value. The first step, the attack of this amine to this carbonyl center is the rate determining. Okay. Now what happens? Now once you come to the other side of the amine center, let's say electron withdrawing group. So electron withdrawing group, we can think of simple fluoro or simple chloro substitution, or and then cyano group we can think of, or we can think of nitro group we can think of. Now what happens when you have electron withdrawing group? The first step, that is attack of this NH2 group to this carbonyl center, is no longer rate determining step, because it will have high positive charge kind of thing here, because X will be electron withdrawing, right? So this attack of this NH2 group to this center is very fast. I mean, it is so fast that it is no longer rate determining step, so it doesn't matter at all. So if you have a AFCl or cyano or nitro, it is not the rate determining step, so it will attack very fast. Okay, so there is no effect. Now what happened? The rate determining step changes the dehydration step. Okay, now the rate determining step is the dehydration step. Now in the rate determining dehydration step, it will be disfavored by NO2 group, because there is a positive charge will be formed. Let me show you how it will be the case. There will be NH and whatever else, okay, and there is OH. Please, I think you know the mechanism, so I am not drawing the full thing. Here is a pH, okay, or AR group. So here there is a lone pair of electron. I am showing negative charge. So this will push it here, and OH will leave. Not as OH, OH2, H plus in presence of H plus H2. So NO2 group will have slightly lower rate than the fluoro, than the chloro, than the cyano. So it will have a negative slope of slightly tilted, not as large. Okay. So this will be NO2. So you see, when there is electron releasing group, like extremely releasing group NH2 OMe, slope is like positive here up to hydrogen. When you move to electron withdrawing group, the attack is no more rate determining step. Now the rate determining step, the dehydration step, which is this step. Now here, what will be favored? Little bit electron releasing group, not releasing comparatively, like fluoro, chloro. This will be little bit faster compared to the NO2 group. So that's why we see a plot like this. Okay. So rho value is around plus 4 point something and then minus 0.25 kind of something. If you see the slides by ma'am, I mean in the class, you can think, and also I have also discussed this. Now I will show you the slide directly taken from the class. So this reaction, rho value is 3.5 for electron releasing group. Please try to understand why this is the thing. And if you go to electron withdrawing group, minus 0.25. Okay. And I would also urge you to think about why the values are so different, like plus 3.5 and minus 0.25. See, when there is electron releasing group, the attack is on the carbonyl center, which is very adjacent to the benzene ring. So there is a direct effect. And in the elimination step, it's a simultaneously you can think of lone pair is coming and OH is leaving. So there is not so direct formation or accumulation of charges. So that's why it is a less impact compared to the releasing group. I hope it clarifies your doubt on this question. And let's go with the second question. I mean, not second question, next question. This falls along with the similar concept with the earlier one. And again, I will give you some time to think about it. Please read the question and answer it in the chat box. Here there is a change in mechanism itself. There is a change in mechanism itself. In the earlier case, there was the same mechanism, just the rate determining step was changing from first step to second step. So for the given reaction, the rho value is found to vary depending on the nature of the substituent due to change in the reaction mechanism. The substituent X having negative rho values are which one? this is directly question from Clayton or any other book. You can find this example. Now, if you okay, let me give you some time and then I will come. Guys, answer chat box. Pallavi, nice. OME and NH2, very good. Anyone else? Okay, that's great. Now you see, a electron releasing group will increase the rate. Yes, perfect. So here you have to understand one thing: the change in mechanism. Actually, what is the case here? I will go to the slide and then discuss here. Now, the interesting see thing that in the last example, it was similar to the carbonyl group attack, right? If you see the question, where is the question? If you see this question, here I was saying that when there is NH2 group, the rate will be like NH2 or methoxy group. The attack of this is little impossible or difficult. That's why it was the rate determining step, right? It's NH2 group, it will have push electron density here, and then the carbon center will have much higher electron density, so attack is less favored. Now, when I come to this example, here you see, uh, you see, there is a drastic change here. I mean, altogether it gets changed here. So these four substituents are there. Okay. Now let me discuss the electron releasing group like methoxy and NH2 group. Now what happens is there, see there is a chloro group which can leave actually. In the earlier case there was hydrogen. Compare it here. So there is hydrogen. Now you see here there is a chlorine and it changes all things. So what happens when you have NH2 and methoxy? Just a second, I have a friend. Okay. So please Deepa try to add little early. And see that how it gets changed. Now let me draw it, otherwise it doesn't make any sense. Clear the frame and I will get I'm having difficulty with this mouse. So AR group and then CO and then there is Cl group here, fluoro, right? Now when there is NH2 group or methoxy group, basically it will what happen, the NH2 group will push its electron and the chlorine will remove, I mean it's act as a leaving group. In place of, if it is the hydrogen, do you think it will happen? No, it won't happen, right? So what will happen here actually is quite a bit of different thing. So this is the rate determining step here. So there is a, so this AR group is here. Oh my god, what I am drawing here. Sorry. So this is the case here. So when there is NH2 group, methoxy group, or any electron releasing group, it will push the electron density. I mean, and then there is a leaving group tendency. The Cl will remove, and this is a formation of this carbocation type structure. Now, what do you think? Which will be much more favored? This formation NH2 methoxy, cyano, or CH group. Of course, when there is NH2 methoxy, these will favor formation of this, not the CH group, right? It won't increase the electron density and thus it cannot remove this chlorine atom, right? So what happens is that there is a drastic change here. Now here, if you plot the thing, that NH2 group will have in the topmost position, right? I'm not drawing the X and Y, what is. Now then there will be methoxy here. Now there will be a methyl group here. So as you move, if it is more electron dense releasing group, the formation of this is the faster, right? So you see the rho value is negative here. Now if you see the compare with the earlier one, it was a completely different situation. Electron releasing group was having rho value positive one. So see that this is the beauty actually. So And then suddenly what will happen? It will come to hydrogen, let's say here, and when you go to CHO and cyano, this no longer forms. So altogether different mechanism. And when you go to CHO and other thing, this will not happen. This living group concept which we were saying earlier, this is not the case. There it becomes normal, the previous situation, that water will attack here, and then this there will be tetrahedral intermediate formation. Don't forget to make the tetrahedral intermediate. I'm not drawing. And then there will be intermediate, and then Cl will leave. So when you go to electron withdrawing group, the mechanism itself is getting changed. There is no longer formation of carbocation. There will be different mechanism. Now what do you think, if there is CHO or NO2 group, which will be highest? NO2 will of course have highest rate here, and then the before it will be CHO, and before it will be Cl, because NO2 will be more electron withdrawing group and the carbonyl carbon will be more positive charge. So when it is NO2, it will be much faster. So the plot it will be look like this. So see that it's a complete reversal of the plot of the earlier cases. So this is the situation for this mechanism, and what we have been asked, the substituent having negative rho value. So of course the answer will be this electron releasing group like OMe and NH2 group. I hope this clarifies your doubts on this question, and it's pretty interesting. These examples are everywhere you will find it. It's very important. So this is the question. The substituents having negative rho values are methoxy and amino group. Nice. So let's go to some other question. So this is based on primary kinetic isotope effect. Again, I will give you some time, and it's not that difficult. It's very easy. The reaction that show a primary kinetic isotope effect or isotopic substitution of marked hydrogens is are. So you have been asked which will show primary kinetic isotope effect. You have given 4 options. Let me give you some time. Anyone answered? Let's check it. Please answer it fast. Which options will show primary kinetic isotope effect? It's very easy. Anyone answered? Option 1 and 3. Anyone else? Sonia, you can answer, and then Deepa, Dharani. You can try, it's not a big deal. You have solved, I also think. Primary kinetic isotope effect shown which reaction? And if you answer, just try to say because of this, because of that. And all this mechanism I have shown actually. In the last class, I talked about this third reaction, benzene, and this aromatic electrophilic substitution. I have talked a lot of time. First is elimination, second is also elimination. Okay, Venkatesh, you are able. Pallavi, 1, 2, 3. Venkatesh, option 1. Option 1, base attack the hydrogen. Yeah, I mean, that's how you should respond. Okay, with the proper why you say this. Yeah, Pallavi, why do you think 2 and 3? Lavanya, you can also answer sometime. Option 3, NH2 ion attack the hydrogen and remove it. Yeah, perfect. That's good. That makes the answer clear. So, so the if I say the answer directly, it is like option 1 and then option 3. And why not 2 and 4? That I will say first. Why not option 2? Because it follows an E1 mechanism. Why E1 mechanism? So there is a tertiary carbocation formation. So basically carbon bromine breaking is the rate determining step. So remember I am talking option 2 here. So there will be plus charge, and in the second step hydrogen will break, carbon hydrogen will break. So there is a carbon hydrogen bond breaking is there, but it's not the rate determining step. So we won't see any primary effect. So there will be effect there, but that won't be primary kinetic isotope effect. And the question explicitly say that primary kinetic isotope effect. So that's why second option will be not the correct. So there is a carbocation formation and the rate determining step doesn't involve CH bond break. So 2 is not correct. So that's a small thing to understand. And in the option 4, it's not at all. The carbon hydrogen bond is not breaking in the rate determining step. Actually, it is getting breaked. See, first step will be the pi electron attacking the electrophile NO2 plus. Now, in the second step, the hydrogen carbon hydrogen bond will break, but that is not the rate determining step. That's why again it is not the case. Primary kinetic isotope won't be seen. Now compare with the first and third. First, what will happen? The ethoxide ETO minus will directly and simultaneously carbon hydrogen bond will be break. There will be double bond formation. Bromine will be leaving. So overall, in the very see, it's a single step elimination E2. So here the carbon hydrogen bond breaking is involved in the rate determining step. So that's why we can think of primary kinetic isotope effect in the first reaction. And if you come to the third reaction, this follows the benzene mechanism. Like there is a addition elimination mechanism. There will be formation of benzene. Now benzene involves this carbon hydrogen bond breaking as the rate determining step. So NH2 minus will attract this hydrogen and the bonding electron pair will come here. It will attack here and then Cl will leave. So in the rate determining step is involving CH bond breakage. So that's why again it will show primary kinetic isotope effect. Overall, option 1 and 3 is the correct answer for this question. Why not 2? Because it follows E1 and there is not rate determining step in which CH bond is breaking. I hope this clarifies this question's answer. Okay, now let's move ahead. It's 50. I have 10 minutes more and more question. And again, a question similar to kinetic isotope effect. It's a simple one. Please, I'm giving you some time and just make sure you answer it properly. Guys, those are not answering, please try to answer. If you have any doubt, you can write it in chat box. If I know the answer, I will try to say it as clearly as possible. If I don't know, I will try to see it and come back to you. A is a elimination reaction. B is a cyanohydrin formation, carbonyl group attack. This is the first. In the first very beginning I talked, and the third reaction is a pericyclic reaction where there is a elimination of nitrogen. Few more thing. In the first reaction, there is a carbon hydrogen bond breakage, and in the second reaction, there is no hydrogen is breaking. Third reaction, no carbon hydrogen bond is breaking. So obviously B and C can show primary kinetic isotope effect. Only A can show primary kinetic isotope effect. So and A is a typical elimination reaction E2 where the carbon hydrogen bond will break, formation of double bond, leaving group will leave amine in Me3. So of course A will be 3, primary kinetic isotope effect. Now the interesting part or difficult part is that B and C, which is uh, both are secondary because there is no carbon hydrogen bond breaking is there involved. So both are secondary. Now what is the next question? Whether it is inverse or normal. What is the difference between the two reaction? In the B, option number B, you see formation of from sp2 to sp3, from tricoordinate to tetracoordinate formation. When you come to C, it is from tetrahedral to trigonal planar. So from sp3 to sp2. And typically these are the cases how they will explain, though there are actually not the case like sp2 sp3. This is, it makes it little easy to understand. And there are, in the potential energy surface, there are difficult things. How the energy difference between carbon hydrogen and carbon deuterium bond is changing will affect the main thing. So let me see the answer if some of you have done it. Sir, why it is secondary? Secondary Pallavi, because there is no carbon hydrogen bond is breaking is there. For example, can you draw the mechanism actually? Let me show you. देखो कहाँ चला गया? Dear friend, see in the third case, let me show. N2, I'm saying just N2, okay, ignore the other thing. And there is hydrogen, two hydrogens are here, two hydrogens are here, and something is I'm missing. Let me check the question actually. There is a one double bond here, okay. So there is a double bond here. Now let me change the color. Now what will happen? This, there is arrow here pushing here, there is arrow pushing here, and N2. So overall what will happen is that all I get is an diene actually. So the hydrogens which are here, the hydrogen which were there is actually retained, like CH2 is itself is here. So no carbon hydrogen bond is breaking, so that it cannot show primary kinetic isotope effect. The very idea of primary kinetic isotope effect, that in the rate determining state there should be carbon hydrogen bond breaking. But you see in this reaction there is no carbon hydrogen bond breaking is there. Similarly, in the second option number B, there is a carbonyl group and then aldehyde is actually there. So hydrogen is there here. But you see the right side, product side, this hydrogen has not broken. Cyanide has attacked here and then O minus is formed, which is get protonated, and OH formed. So overall it's a tetrahedral product is formed. So there is no carbon hydrogen bond breakage. So that's why it cannot show primary kinetic isotope effect. It must be secondary isotope effect. Does it answer your question?
Yes, sir.
Thank you. Now I have none of you have answered. Okay, Deepa has left, no problem. Anyway, so let's see the answer of this question. So it's very easy to, mnemonically it says that from, if I go to sp2 to sp3, see sp2 to sp3, it will show inverse secondary kinetic isotope effect. Whereas from sp3, CH2 was sp3 here, it is going sp2, it will show normally secondary kinetic isotope effect. Now I look for, so there are so many ways to explain this, but I like the simplest one, which I have written here. You can note it. It's from Carey and Sundberg. This statement is, so you see, an inverse isotope effect will occur if coordination at the reaction center increases in the transition state. So if it is increases in the transition state, the bending vibration will become more restricted. Now question is, do you understand the second point? The bending vibration will become more restricted. This line is actually important. Okay, bending vibration will become more restricted. Now let me explain this. It's a typical simple answer, that's why I'm saying. Come to this reaction. This is carbonyl bond, this is hydrogen. From sp2, cyanide will attack here, and it will, a transition state will have 4 species around carbon, right? So it is come from sp2 to sp3, from trigonal to tetrahedral kind of species. Now this CH bending, so there is the one vibration involving this carbon hydrogen bending. See, if it is got more, there will be more steric from trigonal to tetrahedral, right? So there will be more steric, steric interaction. So now bending, carbon hydrogen, there will be bending vibration, it will bend. Now, what do you think, which bending will be much easier, carbon deuterium or carbon hydrogen? See, carbon deuterium bond length little small and deuterium is smaller, and carbon hydrogen is little bit larger. So the bending is, restriction will be more where carbon hydrogen bond, carbon deuterium is short, so less restriction. So that's why the bending vibration will become more restricted. So the rate will be little slower compared to carbon deuterium. So that's why we see that the B will have inverse secondary kinetic isotope effect. That is, deuterium will be little faster. If you have deuterium there will be little faster compared to carbon hydrogen. And why I say this? Again, the bending vibration will become more restricted for carbon hydrogen compared to carbon deuterium. And you can read it much more in the other books also. Now let's go to other question. This question I will directly jump to the answer. What is happening? It's a Claisen rearrangement. Pi bond is coming here, and then the sigma bond is breaking here. Not Claisen, sorry. It's a similar version. It works in a same way. Claisen in the aromatic version, it is same, I think. So this sigma bond will break, and then this pi bond will come here. Overall, you get this. Again, you see there is no carbon hydrogen bond is breaking here. Carbon bond is breaking. So we don't expect any primary kinetic isotope effect. So this option number 2, observed primary kinetic, no kinetic effect is observed. This is also not correct, because there is some involvement of this hydrogen here, because there is a change in hybridization from sp3 to sp2. So again, we expect a secondary kinetic isotope effect. So secondary kinetic isotope effect. And what is else? From sp3 to sp2 formation, so we expect normal. So kh is greater than kT. So 1 and 4 is the correct answer here. Now next, what question we have? Again, this is a simple question. This is earlier I have discussed. People, guys, everyone, answer it fast, okay? E2 mechanism, do you think it is E2 mechanism? No, it is not E2. The reaction follows E1. Yes, it can follow E1, carbocation formation. CH bond breaks in the rate determining step. No. CBr bond breaks in the rate determining step. Yes. So option number 2 and 4 is the correct answer. Okay. So the reaction follows E1 mechanism and CBr bond breaks in the rate determining step. And I will stop with this reaction, and let's see. So I think you have answered this question in your assignments. So what will be the intermediate here? It's in the ma'am has discussed in the class. Let me give you some time. If you are not in hurry, please answer this question. Then I will stop. 1, 2, 3, 4. The major product isolated in the reaction of carbon and B with CO2 is which one?
Option 2, sir. Option 2.
Yeah, perfect. Right. So you have answered it. So let me discuss this just by here. See, this negative charge will attack at this ipso position of the benzene ring. And then this pi electron will come to the para position here, negative charge, delocalization, and it will attack the CO2. And then abstract the hydrogen to form this intermediate, so which has been trapped. You can isolate this intermediate option 2. So this is a typical experiment to isolate. Okay. And question is, why not the other thing are observed? That's a little tricky to answer, I would say. Uh, First, let's say why not one. I immediately see that this negative is can be stabilized if it can delocalize through this pi electron benzene ring. So it will attack here and then it will try to delocalize with the benzene ring. So rather than directly attacking here. So there is a chance of that. If it is not the case, it would have directly attacked. Why not option 3? Because it will be highly sterically hindered. Attack at this ortho position with this methyl group and then COOH group. So this 3 is also very difficult to form. And then why not 4? That gets a little bit more difficult to say, because negative charge can come here. It could have been formed, but it attack at the immediate position, which is like para to the ipso carbon. Okay. So overall option 2 is the answer here, which is experimentally found. And I have more question, but it's already 8, so I won't discuss the other question. And within this, if you have any question, let me know. I will try to say. And thank you for joining.
Excuse me, sir. Question number
Yes, Venkatesh, go ahead.
question number
Question
slight
number 1.
doubt, sir. Yes, sir. Yes, sir.
Okay, 1 second. First question you're talking, right?
Sir, yes, sir.
So you have seen this. It's a very easy. Yeah, go ahead. Yes, Venkatesh, what is your problem with this?
Sir, the negative rho value will reflect the carbonium ion intermediate. It is true, sir. It is true in all cases. If the rho value negative, then the intermediate formed will be carbonium ion.
Actually, we shouldn't do like that. Okay, we shouldn't conclude like that. It's better to look at the mechanism and then try to conclude. Okay. But if I strictly, follow the book in Claydon, and it is written like that. There is a chances that there is a carbocation formation. The electron density will be moved from the benzene ring towards some atom. It is like written there. So the electron from the benzene ring, electron will go towards the some center. Yes. For example, there will be a positive charge here, so NH2 benzene ring will have electron density. It will push towards the carbocation center. So it is generally written like that. Anything else?
Yes.
Okay.
Thank you, sir. Very kind of you, sir. Next week, what will be the case, sir? Next week, after exam, any we can discuss.
Okay. Next week, I think I will discuss general acid-base catalysis and some questions which are there. So.
Okay. That is next week is the exam. After the exam, correct, sir? After the exam.
Okay. Maybe. Yes. Yes, Pallavi, you have some question?
No, sir.
Okay. Then I will leave. Thank you, guys.
Yes, sir. Thank you, sir. Thank you. Kind of you, sir.
Thank you.
Thank you, sir.